So I had a few questions from the 5.5 homework, so I wanted to run through these three. And I think for 45, part of the question there was, how do you know how to pick the U on this? And part of it's a little bit of just experimentation. On 45, the U needs to be inside of another function, so that's inside of a fourth. That seems like a pretty good candidate for U. I don't quite see how that's going to work out with the rest of the stuff, but let's try it. Let's give that a shot. So if U is going to be 3x squared minus 2x plus 1, and if possible, I want the whole thing inside the fourth power. I don't want to make U just 3x squared minus 2x and have something like U plus 1, unless I see an easy way to integrate that. But otherwise, I'm going to take everything inside the fourth power. So there's U. Du then just has to be the derivative. So it's just 6x minus 2 dx. And looking up here, I can see that's not exactly what I have. But if I'm off by just a constant, in other words, if I can take this second line here and just divide everything by 2 on both sides, I can get 1/2 of du is 3x minus 1 dx. And then that makes me happy because that is exactly what I have up there. And now when I rewrite the integral, I'm in pretty good shape. I can say what I've got on the bottom is u to the fourth, and what I have on the top is the 3x minus 1 and the dx together make 1/2, and I'll stick the du over here. And probably you'll just factor the 1/2 out front and say 1 over u to the fourth, or really u to the negative fourth du. And from there, you're good to go as far as integrating, and I won't finish that one out. 49, the question was about how do you handle these limits, this 0 and this 2. And really, I should have made this more clear on my instructional videos, but there's 2 ways to handle those limits. One possibility is to completely ignore them until you're at the end of the problem and you're back in x territory. And the other way is to convert them into u limits. So let's talk about both of those briefly. So it seems pretty clear here that u needs to be x minus 1. And then du is going to be 1. So just dx, basically. So when you rewrite this integral, you've got u to the 25th du. And you've got your choice here. You can either, like I said, you can either just finish this integral off, sort of ignoring the limits for the minute, and just saying this will be what, 1/26th u to the 26th, and then replace u with x. So you get 1/26th x minus 1 to the 26th. And this is the point where you say, okay, that 0 and that 2 on the original integral, those are x limits, so I can plug them in now that I'm back to x stuff, right? So I can plug 2 in, I can plug 0 in, evaluate, that'd be fine. So I can do that, or the other option is to say, once I've integrated and I've got 1/26th u to the 26th, I could change these x limits. This 0 is x. It's an x limit. So if x is 0, u is, and just plug 0 in for x right here into this equation. So if x is 0, u is negative 1. And if x is 2, u is positive 1. So you could use this expression right here and plug in negative 1 and positive 1. Notice either way what you are going to be taking to the 26th power. And if you use this version right here, when you plug 2 in, you'll get 2 minus 1. You'll get 1 to the 26th. Here, the minus 1 has already happened, right? So you just plug 1 in for u, and you get 1 to the 26th. And then when you plug 0 in, here you get negative 1 to the 26th, and here you get negative 1 to the 26th. It works out exactly the same either way. Most of the time when I do these, I actually do this this method. I turn it back into x and just kind of ignore the limits in the meantime. But if you want to sort of, I guess, save yourself one step and add one step at the same time, you can leave your integral in u, and then you can do this little conversion up here, and you can change your x limits into u limits. Okay, so the last one I wanted to look at was 69. And 69 has this x squared plus a squared. They point out that a is just a constant. It's some number that's bigger than 0. So when you go 0 to a, you're going forward, not backwards, as far as what it looks like graphically. But anyway, it certainly seems like x squared plus a squared is inside the root, so it's going to be our u. The du then becomes 2x, and keep in mind a is a constant, so its derivative is 0. So 2x dx. And I have, again, I'm looking ahead a little bit, and I'm saying I've got x dx. I have x dx. So just divide both sides by 2. Last step. Last step before we get going on this. 1/2 du is x dx. And I'm ready to make my substitutions now. So when I integrate, x dx becomes, and I'll put the 1/2 out front, 1/2 du. Inside the square root, I've just got the square root of u. And I'm going to just hold on to my limits until I get back to x's. So let's go ahead and do the integration. Let's see, I get 1/2. This will be u to the 3 halves. So I need to divide by 3 halves, which is multiplied by 2/3. So I end up with 1/3 u to the 3 halves. I'm going to remind myself that u is x squared plus a squared. And I need to plug in 0. And I need to plug in a. And keep in mind I'm plugging in 4x. Those are x limits. So when I plug in a, I get 1/3 a squared plus a squared. So 1/3 of 2a squared to the 3 halves. And then minus 1/3 when I plug in 0. 0 plus, I'll just get a squared. A squared to the 3 halves. You can clean up the exponents just a little bit here. I actually don't know what form the back of the book uses. So I'm distributing the 3 halves to the 2 and the 3 halves to the a squared. Multiply the exponents, the 2's cancel. And same thing here. Power raised to power, multiply the powers, 2's cancel. So probably either, certainly on a test, either of those last 2 lines I would consider to be fine. Both of them you've evaluated the integral, right? You've plugged in a, you've plugged in 0. I don't know that the bottom line's much simpler than the top line, so either one would be fine. Okay, so thanks for asking those questions. I'm always happy to make videos about questions.